All right, so in this video, we're going to talk about volumes by cross sections. Now, a couple things before we really get into this. First of all, the big thing is we're talking volumes now. We're not talking area anymore. So we're going to be creating these three-dimensional solids that we're going to be finding the volume of. We're going to be doing so in this particular video by cross sections. There'll be another method that we discuss a little bit later. So this is the method for this section. And then what I have up on the screen so far is a general setup. It gives us a volume, and this being the integral, where the a of x is considered to be a cross-sectional area. Now I'm going to start our conversation dealing with probably the most common case, which is also probably the simplest case. And you'll see what I'm talking about as I draw it, but we'll follow up at the end here and talk about some more specific cases that you might encounter. This is called the Capillaries Principle, by the way. If you're doing any additional research, you can look that up. I also wanted to mention a little bit of additional research because what I'm about to draw sometimes is very, very difficult to see, especially if you're not a visual person, which I personally struggle with a little bit. So I would encourage you that if this is not quite making as much sense as you would hoped initially, continue investigating. Get online, look up some videos, look up some images as to what it is we're doing so that you can better visualize. Once you're able to see what you need to see, it's all going to make perfect sense. But for some people, it takes a bit of time. All right, so the first method we're going to look at is going to be where we take this curve. All right, I've got some curve right here. We're going to call this guy y equals f of x. And I am going to take it now, and I'm going to revolve it around the x-axis. Okay, so I'm going to take this thing, and I'm going to go around the x-axis, which is going to give me a three-dimensional solid. So I'll do my best to kind of mirror image this here at the bottom. And in doing so, that's then given us this three-dimensional solid. Okay, and just like always, my endpoints here, we're going to use an A and a B right there in the middle. And when you look now at this particular picture, having gone around the x-axis, hopefully you're also picking up on the idea that our cross sections, or our slices, if you will, are going to be circles. So if I sketch a slice of this, if I take a sword and I cut through it vertically, I'm going to get a cross-sectional circle through there, which means my area, the a of x, my area is going to be pi r squared. Okay? Now, if we take a look at the radius of this green cross-section, this guy right here would be our radius. Okay? If this is an x value, then this value right here would be our f of x value. That piece right here is going to be our radius. So when we say that our radius is, it's r, but it's really going to be the function squared. So a of x equals pi f of x squared. Therefore, the volume would be the integral from a to b of pi f of x squared dx. Okay? So again, don't overthink it. These formulas are not just made up. They're not magical. There's nothing special about them. We just happen to be looking at the area of a circle where our radius of that circle is going to be from here to here, which would be the height at an x value. Okay? So that's kind of the first easiest way to look at it. The other way, though, is well, what if there are two functions, just like we saw in the last section where we were looking at area between curves? Well, that's really not going to be any different either. I'll try to draw this one a little bit bigger because it's going to have more to it. But if I go ahead and I sketch one curve in like this, and we are going around the x-axis, then I've got another one doing the same thing kind of down here. Now, I've tried to make this work. My pictures never look great. But what if we have another curve in here that does something like that? And still going around the x-axis now, this is going to give us a similar picture, but one that's actually going to have a hole drilled out of it. So So something like that. Where if you're looking down the x-axis, it's got a hole through the middle of it. Okay? So let me go ahead and do some labeling so you can see this a little bit better. This is going to be our A value. This is going to be our B value. And again, the book has much better pictures than I can draw, but at the same time, I think this is should be enough to let you understand that there's going to be a hole through the middle of this. So let's label this top curve here as y equals t. Let's label this bottom curve here as y equals b. Now, the reason why this is going to be so nice is because it's still that same top minus bottom mentality. So for us, the volume is going to be our integral from a to b pi top squared dx minus the integral from a to b pi bottom squared dx. So remember before how we talked about top minus bottom, we're going to get there, but if you think about it individually, we've got our big minus our little, which is going to be the big giving us the entire volume, then we're subtracting out this guy right here. And if I combine this now, we do actually end up with our pi, and then we have our top squared minus our bottom squared dx. So I went ahead and I factored the pi out of both of those as well. And you could also take the pi outside of the integral entirely. But here's our volume now, provided we have a hole drilled out in the middle. Now, the book might call these things two different methods. Sometimes you'll refer to this as called the disc method versus the washer method. I don't really like giving them labels because they're the exact same thing. I mean, we could do this to this guy where the bottom just happens to be the x-axis, so y equals 0. So I would much prefer you view this geometrically as opposed to giving them specific names and reviewing them as certain methods. Now, before we go on to some examples, also note that I could have the same exact discussions with respect to y, but instead we would have a right squared minus a left squared dy, whereas these would also be y values such as c and d. So there's the basic gist of where we need to be. I'll go ahead and clear the screen, get some examples up here, and see how it goes.